ideas, they get very upset. It's a religious, emotional reaction on the subject, although many people come around. And I was wondering why that was true, and I wouldn't be surprised if it was things like this that got people emotionally involved. But more or less, this is, for those of you who aren't car buffs, this is a 59 Caddy, and this is supposed to be a Porsche. I don't know if that was the best example, but at the time, when our research was funded by DARPA, we had a hard time picking a Japanese automobile here. Seemed to set the wrong tone, but maybe a Japanese automobile doesn't have any tail fins. It's light, fuel efficient, could still end up with being a better automobile than something that people had been building for a long time. Okay, so if I gave you the principles for the design of a complex instruction set computer or a traditional machine, what were the guidelines that followed these RISC guidelines? What were the principles that we tried to follow in what we were doing? And sometimes we followed them and sometimes we didn't, but this is what we tried to do. Keep it simple unless there's a very good reason not to. I've heard that said lots of different times. Another good way to say it is use your intelligence to simplify the solution. The 10% rule means generally what architects do is they try and optimize an architecture. They try and add things to it. They're going to reduce the number of cycles it takes to get work done. Unfortunately, and I think in part because IBM announced that the architecture is not the same as implementation, is they tended to forget about how long one of these cycles would take. So the 10% rule is if you come up with a wonderful architectural idea that saves 10% in cycles, saves 10% of the cycles it takes to execute a program, but it increases the cycle time by 10%. Cycle time by 10%, you haven't made any headway. The programs take the same a long time to execute because you multiply the number of cycles by the cycle time to figure out how long it takes to do work. So we made a real emphasis of trying to keep things simple, and a way you can build faster computers is to shrink the cycle time, and that idea kind of wasn't paid a lot of attention to for a while. The other design principle is microcode is not faster than simple instructions, especially for a cache-based execution. As my understanding is the lecture after this one is going to be by Harold Stone, who's now at IBM. Talk is going to be about cache memories, and I think that'll be a nice tie-in to this lecture. But given that caches work well and that we can build caches from the same chips as we can build microcode, we can get that high performance. The other thing that typified the traditional designs is somehow microcode was magic, and I probably, with my research, helped what I was doing after my PhD. I was helping support that idea. Well, we'll just move this software into microcode and everything will be great. But it's not magic. In fact, it's not even that great. It's a lot harder to change stuff that's been moved into microcode. And what's the difference about a runtime library versus keeping something in, especially if you had to put the microcode in ROM? A runtime library for a RISC machine has the advantages of its software. It's changeable. You don't have to fix it before the machine's been shipped. You can change it any time during its lifetime. So this runtime library versus ROM and microcode, it's hard to see if the cycles are as fast, why not keep it in the runtime library? This is one of the areas where people say RISC machines just offload that function from the hardware people into software, and I think I agree with that. But writing a cyclic redundancy check routine like there is in the VAX instruction makes more sense as a runtime library routine rather than something that has to be built into every VAX that's ever going to be made. And the last two principles of design are stick to a simple decoding size. The RISC machines uniformly ignore the advice about trying to make programs smaller so that they run faster, and they reward simple decoding so that they can get better pipeline execution. And we think that's a lot more important than program size. And the last thing is trying to use compilers to simplify, keep the operands and registers so that they can be reused, and deal with loads and stores to memory. That also simplifies virtual memory implementation. So let me show you some of these machines that are the three best examples, I think, of the RISC. First one is the IBM 801 project. This is a real interesting project. They actually had a machine working in 1979. It was built in ECL. I have brought with an art. In fact, let me back up a bit. I think this article's been handed out, but if not, it's the. I'll back all the way out. This is the January 1985 edition from CACM, and it's about computer architecture. And here's a picture of the IBM 801. First picture I'd never seen this machine, so I was real interested to see the picture. This machine is. Let me get closer. This machine was built out of ECL technology. The work that was done at IBM was done in the 70s. It was this machine had a cycle time of 66 nanoseconds, and like I said, it was up and running in 1979. Unfortunately for everybody, the people involved in the project and for those of us in the research community, IBM was unable to talk about the 801. In fact, the first paper was published in 1982, I think in part because of a conference that was organized by a former Berkeley student. He tried to twist IBM's arm to say that they need to publish to get credit for the work that they'd done, and that helped let them be published. But IBM, as a corporation, I guess, or for whatever reasons, decided to sit tight on this technology, and there were a lot of rumors about the technology, but didn't know exactly what they were doing, and some of the articles that were in the popular magazines weren't very helpful. But it was a real interesting project. But there it was. They had a RISC machine working in 1979, and this work was led by John Koch and had the involvement of a lot of people at Hewlett-Packard. But I think John Koch is, if you had to pick one name, that's the name you would pick. The work that came after that for the RISC machine, this 801, is the work in VLSI done at Berkeley. This is a photograph of RISC-II. We had a RISC-I that was a VLSI implementation that was done in 1981, and RISC-II in about 1982. And this is, instead of being built out of boards worth of cards, this is built out of custom NMOS. And we'll come back to this design later. This section, this large black hole here, is the register file. So this is a register-intensive design. This was a very nice design done by two students, Robert Shearburn and Manolis Katavenis. Robert Shearburn's now on the faculty at RPI in New York, and Manolis Katavenis is on the faculty here at Stanford. Shortly, not too much longer after we started our project at Berkeley, there was a project at Stanford. This project is called the MIPS project, and this is their first machine. It was something like 6 months or a year after the Berkeley project. This is, again, a custom NMOS implementation, and when I get to the end and talk about commercial possibilities, this chip will play another role. So let me go back to those machines, the characteristics there. So compared to the previous slide, like I said, the IBM 801 was done in 1979, about 120 instructions. Here are the years for the MIPS and the RISC machines. Fewer instructions that were in the 801, but like I said, the main thing about the acronym is the simplicity of instructions. None of them use any control star. All of the instructions were the same size, and the technology, these were two chip designs, custom chip, and this was ECL, and all of them took the register style of execution. If we contrast that with these more complicated examples, let me just come up here. You can see the numbers of instructions are much higher. The variable instruction size is the big differences, and the variety of execution models. Okay, so those are the examples of the machines. Right. What RISC-I was kind of the blitzkrieg model of getting a chip out the door. These students were taking 2 quarter courses and they had to graduate. So RISC-I was done in, the course started in January, and in June we submitted the chips and got it out the door. RISC-II was done in a more leisurely fashion by a smaller group of people who wanted to make a very elegant design, and that is a real nice chip. And the things I didn't say about RISC-II, put it up again. I like looking at it, but this actually has about 75% more registers, and the control area is smaller, even though it's the very same, and the chip itself is on the order of a third smaller than the former RISC-I. So it was a real nice design. It was an example of, we had a person who knows computer science and a designer who knew silicon very well, and they were able to take their time and do a very elegant design, and that was an advantage over RISC-I. Okay, thanks a lot.
Thank you. Since you can have a large number of registers, and instead of a memory-to-memory architecture, it seems it would be more difficult to implement a multiple CPU computer system.
Okay, let's see if I can do this right. I like to be prepared here. So, just as long as I have a national audience. Let's see. Well, so this is what we've done, and this is what I'll talk about next week. This is the project we're working on right now. This is a poster we used to try and get Berkeley students to take our courses and get involved. But the project we're working on right now is a multiprocessor. And so what we're real interested in, on the order of 6 to 12 processors. We're taking you can think of what we're doing is a step-by-step approach, looking these two machines, RISC-I and RISC-II, kind of looking at the instruction set. This one's looking at exploratory programming environment, in particular garbage collection issues, and at that level. This one, the SPUR project, we're going to try and tackle multiprocessors. As far as we can tell, there's very little about an instruction set design or register orientation that has to do with multiprocessors. Multiprocessors has to do with the sharing of information in memory, or perhaps you're going to use a message-oriented. I guess if you're going to use a message-oriented way of sharing, you might want to do that in instruction set. But we believe RISC machines are nice, fast computers, and if you're going to build a multiprocessor, it makes a lot more sense to build out of fast computers than it does to build out of slow computers. And so we're going to try and work on that, but that's hand-waving right now as opposed to any proof. Our guess is that RISC machines will be fine to use as in a multiprocessor system, but that's work that we're going to do, not work that we've done.